Integral domains lie somewhere between rings and fields. In particular, an integral domain is a non-zero commutative ring in which the following property holds. AB is different from 0 if A is different from 0 and B is different from 0. So there can be no non-zero zero divisors. This implies the cancellation property, which says that if A times B is A times C, then B is C. This is using the distributivity in the ring. And an integral domain is always a subring of a field, which we will construct shortly. So what are interesting examples of integral domains? Interesting examples are the integers, but also polynomials over the integers, or in fact polynomials over any integral domain. Counterexamples, which are not integral domains, are, for instance, Zm, where M is composite, because then P times Q is M, which is equivalent to 0 modulo M, and therefore this is a counterexample. Other counterexamples are the direct product of two rings, non-zero rings, because then we have a zero divisor, or zero divisors, 0, 1 times 1, 0. This will be equal to 0, and therefore this is also a counterexample in which we do have a zero divisor, but also matrices, which can be n times n, or 2 by 2 in this simple example, because then we'll have zero divisors like this. So all of these are not integral domains. In an integral domain, we can have a concept of a divisor. If A times X is B, then A divides B. We also have the concept of an irreducible element. This says that A is irreducible if it cannot be written as B times C. And then we also have the concept of a prime, which is that if P is prime and P divides A times B, then P divides either A or B or both. Note that both irreducible and prime is a generalization of prime in the integers. We can also define a unit. A unit is an element A such that there exists an element B such that A times B is 1. Then A is a unit in our integral domain. Finally, we define the field of fractions in our integral domain, which is the minimal field that contains this domain. So if our integral domain is R, then the field of fractions contains basically A over B, where A is in R and B is in R without 0, with some equivalence relation, which is the standard equivalence relation for fractions, namely that AC over BC is equivalent to A over B. And with this equivalence relation and the fact that R is an integral domain, we have that F is a field. Two simple examples. The trivial one is when R is a field, then the field of fractions is just the field itself. And then the second example is when the integral domain is given by the integers, then the field of fractions is the set of fractions for rational numbers Q.